Thank you for joining. We'll be starting in just a few minutes. And kick that off then. All right. We'll give everyone a couple more minutes to join. And I apologize. I know for those of us that are in the Tulsa area, we're experiencing some interesting fall weather, if you will. So we're having some pretty severe storms, unfortunately, Carl. So hopefully everybody's internet holds out and we get a few more folks to join us. First of all, thank you for joining us, everyone. I'm Jonathan Boyett. I am the president of the ISACA Tulsa chapter. Um, Pleased you could all join us today, especially on a very stormy day for Oklahoma. With that, Carl, I'd love to turn it over to you. Carl, if you'd like to introduce yourself, kind of talk about the topic and dive right into your presentation, we'd love you to go ahead and do so. Oh, and in the meantime, I'll be monitoring the chat or anything like that. Do you prefer questions at the end, or do you mind if they're kind of interspersed?
Oh, please interrupt me. I probably won't try and monitor the chat, but I'll be a full screen here. So just jump in, interrupt me. It's fine. Uh, I'd love it for it to be conversational as well. I'm going to go through a lot of detail, but just if something doesn't make sense or it's confusing or strange, just jump in. So.
Excellent. Thank you, Carl. As I said, I'll be monitoring the chat and I'll go off screen until I'm needed. Okay. Thank you.
Okay. All right. Well, thank you all so much for having me. I'm excited to share a bit about quantum security, computing, and the threat that we all face going forward as these technologies evolve. So let me try and get my sharing going here. All right.
We can
So
see the
quantum
screen.
threats and mitigations. So a little bit of background about myself. My name is Carl Dukatz. I've been with Accenture for almost 18 years now, with the majority of that focused on quantum computing and cybersecurity. I've uh, I'm also the vice chair and will be the chair of the Quantum Economic Development Consortium's Use Cases TAC, which is a consortium with over 180 different members involved in US-based establishment of the quantum ecosystem and communities. Accenture is also involved in the World Economic Forum. We recently published a few papers on quantum for sustainability development goals, as well as Quantum Applications Hub that you can go check out if you want to see some live demos and actions on quantum applications and their runtimes and how they will provide benefits to humanity and not just be a threat, as what we're going to talk about today. So I also did some time, a long time ago, in some of the chemicals and energy field and area. So I'm happy to talk about that too, and experiences as to how this threat will manifest within that context. So we're here to talk about quantum threats and mitigations. And I'll dive right in and say there are two threats that quantum computing or future quantum computers bring to our cybersecurity. They can be categorized as these steal now, decrypt later attacks, and these future attacks where impersonation can be possible. And I'll explain a little bit more detail of how these come to be and what they are, but you can think of them generically as that. That's this problem that exists today, that if someone is sniffing the information that you are communicating over some type of network between yourself and another party, that they will be able to store that. And in the future, with a sufficiently powerful quantum computer or cryptographically relevant quantum computer, be able to decode or decrypt that and see what that communication was. And then when those computers are available, they also have the ability to create encryption keys and methods on the fly and begin to impersonate people and ruin the trust framework of the internet as a whole. So it's a pretty grave threat. It's pretty scary, and it means essentially a collapse of much of the cyber security and the communications methods that we have today at internet scale. And so it's worth noting that these advancements. These are advancements in classical algorithm and computational hardware. Also can lead to weaknesses in cryptography that we're concerned about too. But today we're really going to talk about the quantum threat that exists. So there are three general mitigations that can be put in place to protect ourselves against this threat of a future quantum computer. The first one is pre-shared keys. So this is our ability to share keys out of band of the communication channel that we're using to connect to one another and leverage that secret information to then establish a connection. Now, the problems with that is that it can be hard to do this out of band channel and communications at the scale that we need or that we expect for our applications and connectivity today. And so while this will help in certain scenarios, and it's technology that's readily available and that we're using for certain core routers or certain VPNs or other types of systems, it's not going to be scalable for what we use as the World Wide Web today. So that's why we have step 2 here, where we have these post-quantum cryptographic algorithms, or this is what we're calling them. This is a set of algorithms that replaces the algorithms that we use, however, are resilient to future quantum devices. And so these algorithms are not new. NIST has been running a competition for the past decade to derive and to compare and to evaluate the best possible algorithms that we could replace our current algorithms are. And the ones that we're using are from the 70s. And so finally updating and replacing those with some new ones that are resilient to future quantum attacks that are expected to be scalable to internet capabilities. Then finally, the third way to protect against these future quantum computers is to use quantum physics itself and establish quantum communication channels. Instead of just classical bits going over a wire, we're actually send quantum entangled information that, when looked upon, will break in a sense that it will decohere or collapse, and you'll be able to detect if an eavesdropper is attempting to siphon out or take your information. And so these are the high-level solutions to this problem of a future quantum computer.
So, Carl,
Yeah.
how far out do you think we really are from this being a potential or even a significant risk? Like, is this science fiction at this point, or is this in 5 years or in 10 years, or how long? What are we looking at as far as the risk landscape goes?
Yeah, so Gardner just put out some guidance that said they suspect by 2019 that devices, quantum computers, would exist that could potentially attack some of this cryptography. I'm also going to show a bit later a calculator that we built with MIT that allows you to dial in the factors based on what you know, based on different quantum computers that are available, their roadmaps to getting better and scaling, and the error correction codes and the algorithm sophistication. And you can draw up yourself your own conclusion based on that information, based on whether you want to look at an IBM quantum computer or a Google one or an IonQ, the different types of devices, and build your own roadmap as well. But the part of the challenge of this is that we don't know. This is kind of the opposite of Y2K, where we knew exactly what that was, but we didn't know what it was going to impact. And so we had to go run around and try and fix everything. In this particular case, we know exactly what it's going to impact, but we don't know when exactly it's going to happen. And so that leads to this frustration in timing. How much do you mess now, and when do you get started? And so we'll try and as we go through this a little bit more, we'll try and make a case and give you guys a feel for how this is evolving and what to expect.
That's
But
great. Thanks, Carl.
yeah, no problem. And again, if there are other questions, please just jump in and interrupt me.
I will.
Yeah. So underpinning these three different areas of solutions that we can put in place to protect ourselves against these future quantum computers is a concept called crypto agility. And what this is that instead of replacing these algorithms individually in each application. We want to replace where the algorithms are with code that allows us to change the algorithms more efficiently. Because I mentioned that NIST has just come out with and so we're going to focus on post-quantum cryptography for this discussion, but I mentioned that NIST just announced, I guess I don't have this slide in here. Yeah, here we go. NIST just announced the actual finalists that they selected just in August, the first 3 replacement algorithms that we're going to use in order to protect ourselves against these cryptographic criminal attacks. So they announced those 3 algorithms, and then they also just recently, a week ago, announced a set of 14 new candidates that they're evaluating as well. So it's not just about updating to these new 3 algorithms, but also the considerations for additional algorithms that are going to come into play. And that's where this concept of crypto agility comes in, the ability to switch between the most relevant algorithm, the most efficient algorithm in a particular context so that you can gain the most assuredness of security. So what algorithms did they release, or what was selected? There were 2 types of algorithms selected, and not surprisingly, one helps protect against this steal now, decrypt later, or this exchange of on-the-fly keys, and the other one helps protect against where we're using identities or establishing long chains of identities and chains of trust. And so the updates to those methods will allow us in these 2 areas to protect against the attacks that we see from future quantum computers happening. This is a key point because it's going to play out through the rest of this talk, where in one facet, we're trying to protect now against data being stolen. And then another facet, we're trying to protect against these identities that, although maybe they can be stolen today, they won't be relevant because we rotate that PKI infrastructure, we rotate those digital signatures often enough that if you broke one today, it wouldn't matter because you wouldn't be using it later when the quantum computers exist to cause a problem. But the keys that we are using at that time do have to be swapped out for newer keys. So I'll dig in a little bit deeper into these digital signatures versus key encapsulation mechanisms as way of an analogy. So if you have a safe has steel walls, it has a lock, and it has a label. And we use the steel walls to protect the information that's inside, the lock in order to obviously get in and get out, and the label to know whose it is or identify it. And you can liken that to how our encryption works today, specifically how our TLS encryption, our transport layer security encryption works, where there are 3 algorithms being used in any of those communications. So the communications that you use to authenticate and go to a website, the communications we're using on this Zoom call, communications that you use to send an email, they all have some facet and elements of these 3 components when it's transported through TLS security. And the symmetric key is the part that is actually not, we're not concerned about that from a quantum computer being able to break it. However, the lock and the label are at risk of these quantum computers. And very conveniently, the algorithms that NIST selected, one is for the lock and one is to replace the label. And so currently we use AES, the Advanced Encryption Standard, for the steel walls. We use elliptic curve Diffie-Hellman for the lock, and we use RSA for the label generally across the internet. And what we'll need to do is replace these locks and labels with Kyber, now being called ML Chem, and dilithium, which is MLDSA, another name for it. And by replacing these locks and labels, we can then not be concerned about people stealing the information, harvesting it now and decrypting it later, or impersonating the identity of who owns the information or where the information is coming from. So another way to look at that is If an attacker comes to steal the information, and they sit on it for a long time, then eventually they'll be able to get your secret recipe or key information, PII, or the like. And so by replacing this lock, will ideally make it so that even with a future quantum computer, you won't be able to break that particular encryption code. And then on top of that, we'll want to put in the crypto agility capability so that we can change the lock whenever we need to a different lock. Because this is happening on the fly, every single time you do a connection, it's proficient to replace these locks immediately, because it can have an immediate impact the on the communications that you're doing. And on the opposite side, the labels that we apply to the information, these are the PKI infrastructure that we issue trust through, and we sign certificates, and they come through trust authorities, and they're passed down and signed and distributed at through this public key infrastructure, and we rely on that in a different way. And so identities aren't just used for a single communication and then thrown away. In most cases, a key or a digital signature will be issued with a certain expiration time. They used to be really long. Now the industries have kind of settled on 2 years or 1 year, and there's even a push to get them to be reissued every 90 days or so, in order to improve the security behind and the validity behind the identities. But ultimately, when we look at this timeline, say roughly, I said 2029 earlier, 2030 timeframe, you'll need to have this, the RSA will be vulnerable to these future quantum computers. So over the next several years, you'll want to slowly add the new protections so that you have full coverage by the time you reach 2030. And so updating your digital signatures and who they're issued to will be important.
Carl, one thing you had
Yeah.
mentioned early on was the idea of the hack and keep, basically where you're keeping the data. Of course, there's not really a good protection for that, right? Because if for some reason someone steals from us now, when they have quantum, they will, in theory, be able to decrypt that with limited difficulty, I suppose.
Yeah, that's exactly right. So it is absolutely a threat today, and it is part of this whole discussion of where do you add coverage, how much do you protect, what is concerning, what's your risk of that attack happening, and how does that play out for you as a protector of information. So we'll talk a little bit about the activities that are required there, but first is having a strategy for what to do about this. And then the second is having an inventory of where all this cryptography is being used. And that allows you to then walk through from a risk perspective to say, this is where my data is, this is the application it's using, this is the cryptography that application is using. I'm going to upgrade that specifically to protect against the threat. Whereas in other scenarios, it may be just a public facing website where the information, if it's decrypted in 5 years from now, it's not going to really cause any harm or do any damage. So
Overall, that knowledge also helps us with communicating this risk to our leadership levels as well to say, hey, if you're not worried about anything that's being transmitted now being decrypted, then maybe you're not as worried about this risk. But if you're communicating things that are sensitive, which some of us I'm sure are, then this is a risk that we have to at least be aware of and acknowledge.
exactly right. Yeah. This is a technical version of what I just explained. This is the TLS stack and where these algorithms are used and how the negotiation occurs. So you don't actually change TLS, you just change the algorithms that TLS is using. And so you have to source these libraries from somewhere. If you are a government agency, then you may be sourcing them from a company that is providing a closed source version of this, but will provide support for it. If you are a private company or a product vendor, you may be sourcing it from one of the open source implementers or enablers of quantum secure algorithms like libOQS. And I'll show some examples of that as we get a little bit further, but ultimately, here's where the rubber meets the road from a TLS perspective and what needs to change. So if looking at a typical enterprise, it runs about 1,000 applications, and 30% of these are integrated in some way. And so even if you did your central IT put post-quantum security measures in place for all of your certificates and all of your key encapsulation mechanisms, that would and made their interconnectivity work properly, you would still need a lot more help from external entities, from vendors, from patches, and from updates for bespoke systems or systems that aren't fully connected. Additionally, today, the best we have, at least for internet-facing websites, is 82% of them are using cybersecurity now, or at least HTTPS at this point. It goes back to the original point that we were just talking about, though, is that maybe this unencrypted information doesn't need to be encrypted because it's not going to be really at risk of an attacker doing anything with it. What is important to understand that there is a push for us to use encryption everywhere, and the rationale behind it is justified in many cases. But this is where we currently sit. So you may not expect to have full coverage everywhere. But I want to take this view and kind of change it based on what we know now. So what we know now is that everything is subject to steal now, decrypt later using a quantum computer. So the things you thought were protected are now not necessarily protected, as well as at some point, this quantum day, Q day is what they're calling it, is the day that there will be a cryptographically relevant quantum computer. Everything could be, all of our identities will be broken from the threat to factoring. And that leads us in an even worse place where it's not just identity theft, but unable to trust communications over the internet. So this is now the world that we live in, and we have to figure out how to cope and deal with this. So the first step is starting to protect these communications that we're using today. We're using Zoom for this particular call, and Zoom has taken some actions, I believe, to add post-quantum security to certain of their calls and add protective measures. Likewise, Signal, the chat message, or Apple iMessage has added protections. Browsers have added support for some of the algorithms as well. So Chrome, Firefox, Edge all have the ability to enable and use post-quantum cryptography for those particular communications, or for certain communications. But the server side also has to be updated so that TLS stack can negotiate both ends and start to use the algorithms. So the question for a business or for an enterprise is, what is at risk and how much do we cover? Where is the immediate need for implementing these key encapsulation mechanisms so that we can be safe from this harvest now, steal now, decrypt later attack? What percentage of our communications and enterprise do we need to cover? That's kind of the first question that you need to ask. And there are different architectures for how to implement it. It's maybe not just at the web service layer, but you may implement it at the network or routing layer, or layer 1 or layer 2 communications. You may do it at a tunnel layer, an IPsec layer, higher up in the stack as well, a virtual private network. So these are all considerations, but there should be an urgency in identifying where this information is and then adding the protections accordingly. So yeah, understanding what the acceptable risk is. Then the next piece of this is, what is the transition going to look like for public key infrastructure to upgrade? So this is the reissuance of all the identities that you that you currently have, all the systems that have been deployed and registered that may have public key information on them, all the users that use it. It goes as far as every badge card or every smart meter or every IoT device is communicating back to the central hub in some way, and or to one another in some way, and will have to be considered so that you can validate that they are essentially the device you expect them to be. So there'll be a transition period here, and your objective will be to complete this transition and upgrade everything before our wonderful Q-Day or cryptographically relevant quantum computer is available. The risk is that Q-Day moves up, as it has slowly creepingly been. As you saw when I created this, we kind of said 2035 for Q-Day, but now we're seeing more signals around 2030 being at least a concerning date or a concerning time for these cryptographically relevant quantum computers to start to exist. There's also can be different challenges if you're delayed in getting started implementing the standards. So these standards, they just came out in August, and they are now available for people to use, but not many people have started early, even though we knew what they were going to be for the past couple of years. Not many people have added them to products or considered where to implement them or built the strategy for deploying them. And so the timeline is essentially shrinking on our ability to get everything that we need to get updated. And this is everything. The entire internet, right, needs to be evaluated and considered for adding this technology.
So Carl, just thinking selfishly about my own tiny little world, um, it, implementing these post-quantum algorithms, it's very costly right now, right? As far as time, not necessarily the money, but as far as processing speeds, it will reduce that. It'll add additional lag. Is that again? I'm sure there's a trade-off and there's a discussion that has to be had there. Okay, how far in advance do we get ready? Based on what our hardware can handle and things like that. Is there any kind of discussion or kind of calculus that you've done around that?
Yeah, actually, there's some really good groups that have put out benchmarks and published what they believe the additional computational power and latency is going to be. And while the key encapsulation, the green on this particular chart, does increase a little bit of overhead, it's negligible as far as the ability to use that. So there's really not an incredibly large amount of risk adding that to your existing systems today. However, the digital signature piece is a little bit of a different animal. It's not as though our phones or devices won't be able to do it, but the keys are larger in size, and aggregate places that need to process many keys or key stores are of concern. And that is going to increase the volume of keys, that the volume of the size of the keys. And then they're also being concerned about how those keys are formatted, such that do you have both the known RSA algorithm as well as the ML-DSA algorithm, so that there's backwards compatibility, or do you need to separate those out and run them on separate systems so that you truly decrease the reliance on the old keys and optimize the system for better performance and capabilities. And so I think with the DSA, the digital signatures, there's much more concern, and we're seeing that the technology, although you can get some of that issued maybe through a DigiCert and get some sample keys, it probably won't be as robust and available until around 2026. That's when we're seeing people talk about making that infrastructure actually more readily available. But the key encapsulation mechanisms, the green, is something you can definitely get started on.
That makes sense. Thanks, Carl.
So again, yeah, we're trying to avoid this very dangerous risk and exposure. We all know how attacks work. They can you can get in one place. Typically, you can chain yourself through a network, and it's very bad and concerning. Um,
Carl,
so,
we did have a question come in. Um,
okay.
maybe just a clarification. What did you mean get started on?
Okay, so for the key encapsulation mechanisms, we talked about having a strategy, doing discovery, so you know where all this cryptography is, and then there are steps to get started, like communicate upstream and downstream with the stakeholders that there's going to be a change, downstream and upstream with your vendors or providers that you want and need this technology for your enterprise, and you're going to be asking and expecting them to provide it in patches and updates going forward. So those are all, operational and purchasing and architecture conversations you're going to have. But then also these toolkits, as I mentioned, they're available today. They're in some of the products that we're using right now. And that is available for you to explain and share to your developers so they can start considering how to add them to um, their software, their SDLC, secure SDLC processes, and their management processes of integrating the tools and technology. And then you can also have them added to certain components of your infrastructure as well from your IT administrators. They can add them to an Nginx server or Apache server, or enable them um, as a um, as a service through, say, if you're using Cloudflare um, as a CDN. You can turn on this functionality today already and get started on protecting certain properties. So that's what I mean, on getting started, is there's actions you can take to enable it, the technology.
I think that clarifies. Thank you, Carl.
Yeah, no problem. So, accelerating adoption of this is all about those types of things, and it doesn't necessarily have to be costly if you consider the the time that and who is going to do the work and what you can be expected, or where you're expected to get um, the updated protocols and controls from. Okay, so this talk was kind of designed also to explain product life cycles for certain companies. And I think when we had talked about this before, it was for the energy sector and the oil and gas sector, but wanted to share that there are different things if you're building products or putting them out in the field that you also have to consider. So internet connected devices like phones that are only meant to be out in the field to 5 to 6 years. Well, I guess this has also kind of changed with the perspectives of Q-Day moving up, but you may have minimal requirements to add them in your product today, but they should definitely be on your roadmap for at least for having them available in the next year or two, so that all of the technology gets updated, and when it's Q-Day happens or the risk starts occurring, then in a more evolved fashion, that you're prepared. But if you look at things like cars or vehicles, if you weren't considering adding these features a couple years ago, then you may already be behind and putting products that are meant to be expected out in the field and available at risk of um, the vulnerabilities that can be in place from using the older cryptography, especially as we were just talking about when it comes to the digital certificates and signatures requiring more processing power and larger data storage and capabilities to rotate them at an additional frequency, and also enabling crypto agility, as customers will be starting to expect that. And you can expect soon that there will be additional guidance that comes out with these additional 14 algorithms that NIST is going to be considering for the next phase, that they'll also be pushing this concept of crypto agility as one of the most important solutions. And so this comes into play there. And then finally, for things like medical devices and critical infrastructure that is expected to be out in the field for 30 years, there's major concerns about how to protect those systems and devices from being broken by by these future quantum systems and the disruption to cryptography of actually being able to control them. And yeah, so there's just serious and sustained risk to critical infrastructure here. So I talked a little bit about the discovery piece, and I wanted to just paint this broader picture too, to give you an idea of the scope that most people will face when starting to attempt to go after discovering where your cryptography is. On the right, you see all the different types of sources where you may have data and systems and cryptographic information, keys, different environments, different devices, the connections, the underlying infrastructure running it. It's vast for most businesses and most industries, and it can be, um, you know, thousands of different products that fall under your remit to remediate. And cryptography touches every single one of them. So where do you start? And the idea of building an inventory of this can seem very daunting. There's lots of places that you can go to collect information about the cryptography, whether it is your certificate stores or configuration files for your infrastructure, being able to query your operating systems or devices to get that information. You may already have very well documented set up procedures, policies, and controls that explain exactly which cryptography is being used where, but all that has to be parsed out of documents and put together to understand what the landscape is and essentially where do you start. The good thing about this is what we're finding working with different folks and working on projects is that oftentimes you don't need to do the complete deep dive analysis and identify every single element of cryptography before getting started and before making decisions. People are preferring some of um, the activities where you get a high level understanding of what's being used and map that to the risks of those particular environments, and then move into prototyping and evaluating solutions within the context of specific areas. And so it can be helpful to piece apart the entire enterprise and then focus on the ones where risk is most prevalent.
Carl, to your perspective, yeah, I would assume anything that's internet facing or is communicating over, broader networks, those would be the ones we would really want to focus on first, right? Or is there in your mind like a hierarchy that you would go through to try to do that inventory? Because just like you said, that's a daunting idea, trying to find everywhere where you would potentially be vulnerable.
Mhm. Yeah, so that is a very key observation where ingress and egress points are going to be some of the most likely areas that uh, are of concern, especially in an established and static type network. There are many businesses now that uh, don't operate that way, though. They leverage so much software as a service and so much cloud IT infrastructure that uh, it's not as though you can build those walls and say this is in and this is out. Now that it's very um, permeable. So you have, just on your workstation, you're using OneDrive and you save a file, right? So now that file has been synced to the cloud, and something you thought was static within your network is now transiting over whichever channel you happen to be on at home, at the coffee shop, at the office. Somehow the information is moving, and if it's captured in that transit, then it's subject to harvest now, decrypt later. Um, and just like the ways of working now with remote working, yes, there is some return to office, but people are still generally out in the field or out at different locations, and that creates this distribution of communications. And so you can't always pinpoint what is ingressing and egressing from workstations or systems, or which cloud backup is going over which channel to another cloud backup, with how the distribution networks, where the endpoints of those servers are actually located in order to service the potential thousands or millions or billions of people coming to your websites. And so the infrastructure is very complicated, and making the decisions about those walls can be very challenging depending on your business.
So, Carl, I hope I'm not jumping ahead. But maybe you're planning to cover this, but you brought up third party, and honestly, for some of us, that's just the bane of our existence. So, when you talk about third party, how do you make this case to them? Because I've always said that with a third party, it's not just a partnership, it's more of a marriage, right? I mean, your data is their data and their risk is your risk. So if I'm doing the right thing and I'm updating all of my protocols and all of my algorithms to be post-quantum ready, how do I don't know, put pressure on, gently nudge my friends that I am in this partnership with to do this?
Hmm. Yeah. So, same as you would in most other contracts, there can be like a negotiation about when you're re-upping and what risk to take. But ultimately, it is a challenge to say we want to hold you by this new requirement, especially if you're not subject to a legal implication. Now, there are things that are going in your favor, right? So these are the new standards. They are public now, they're adopted. You can point to them and say, this is what is required for security. You as an entity having to work with, say, a national government or federal agency, they are required to adopt these now. And so they have to they've already started, they've already done inventory, they're starting on scoping and remediation, and they have a deadline of, I believe it's 2035. I don't know if they'll revise that now or not, but they have to be using it. And so now you can no longer interact with the federal government unless you make the changes to these new algorithms. So that kind of forces everyone to be in the same boat. Another thing that you can consider is that the um, uh, when there is a case where you're not going to be able to get a patch, or you're not going to be able to get an update, there are architecture models where you can encapsulate whatever that system is, and then it will become covered by post-quantum security, even if the particular vendor or service provider you're working with doesn't want to provide those updates. And that mainly provides control for systems which you have full coverage of. It can be very hard to do that with a cloud service that you're providing on, that is being provided to you. But it's still possible, if you're using a cloud service and you're managing infrastructure within that cloud, to add kind of these networks and capabilities. Well, you have to
Gotcha.
architect them, and it can come at your cost. Uh, Luckily, I know that the CSPs and the hyperscalers are all working to add these components and capabilities within their systems already. And they may not be available when you hit deploy instance right now, but they're taking this very seriously, and they understand the implications. So, for example, I believe it's AWS Transfer Family. So if you're moving bulk data in and out of S3, they have already added the capability to use some of these post-quantum cryptographic primitives in order to do those data transfers, as an example.
That's great to know. Thanks, Carl.
So a lot to consider here, but you don't have to pull everything from every single one of these sources. You kind of want to get a feel for what's here and where you'll need to make the updates. I wanted to talk through, just a specific example of where this may live, and why it can be complex. So if we look at the energy sector with transmission, distribution, and generation, in generation, you may have a whole slew of different technologies, and then within your command and control center, you have a SCADA system, and then that SCADA system is going to have a local server, and then the local server is going to have a PLC, and then that PLC is going to have Modbus, and that Modbus is going to need to using TCP/IP and be able to update to a post-quantum algorithm. So this can be deep within your infrastructure as well, and depending on the system, you can't be expected to manually update this yourself. You're going to have to rely on the ecosystem to move it forward. And so, your question was extremely important, right? Yes, there are some ways you can encapsulate this local server, maybe on a network, maybe in a VPN, but inevitably, as these technologies, as you update the technologies, as you patch, as you remediate and resolve them, you're going to be looking for people to provide you as well with the packages and tools to get everything done. Okay. So here's some examples of different patterns as well. You can see here we call out encapsulation. There's configuration patterns that you can do. And then there's also code that you can update specifically or manually in order to make sure that the PQC algorithms are included. Here, I also mentioned a couple. So some are post-quantum cryptographic algorithms. Others are post-quantum pre-shared keys, or PPK. So this is the idea of you're doing this out-of-band exchange of certain key information so that you can directly connect without exchanging that information inbound or in-band, and that way you're not vulnerable to the steal now, decrypt later attacks that you could be subject to. And just some key quick actions. So key encapsulation mechanisms is kind of the most urgent today for the steal now, decrypt later, and it's done for every communication individually, so you can work to implement this and upgrade it. There are key encapsulation or key management interoperability protocols, which, if invested in and matured, then can provide a massive accelerator. You may be using some of these already. The PKI is your infrastructure that you have today, or the vendor that you get certificates issued from is a great place to start to understand your inventory of PKI and where that's being deployed and used. So you can consider that almost as a quick win, but there will be a long shadow IT inventory, and it will be challenging to sort all this out and find it all. So NIST has standardized the finalist, and I guess this also needs to be updated that although some of the browsers do have the post-quantum cryptographic algorithms in them, it will be around 2026 when we can actually get some of the new keys. So after this, I have a series of demos that I can show with some of how this technology is working, and to show it on the fly and let you get a taste for what it is, if we'd like to do that, or we can just answer some questions.
Sure. So far, we don't have any additional questions that have come in. If you want to go ahead and share your demo, that's great. We've got another roughly 11 minutes. So yeah, however you want to do it.
Okay. I'll start with this one because I want to make sure we get to it. So I put a link in the chat, and you can go check this out. This is a website that we've created to allow you to play around with and test out these post-quantum cryptographic algorithms directly in your browser. I'll share my screen here. So if you navigate to this site, you'll get something that looks just like this, maybe, or it'll be all red and say you're at risk. And what this site is doing is, based on the connection to the site, it's telling you, is your browser already using post-quantum cryptographic algorithms? So in this case, I am. It's detected that I'm using these Kyber algorithms, which are now obsolete because NIST came out with the new standard. And so the new standard has a slight tweak to these, but they're still relevant in securing you against harvest now, decrypt later attacks. So we'll be looking for this MLChem update. And this goes through and explains to you what it's looking for, how it's detecting it, and if you have Firefox, how to enable it, but you can also enable it in Chrome and IE if you haven't enabled it there already, or if it's not turned on by default. It also goes into some more detail about the connection here and how this site is set up. It's written in Go and how it's detecting the connections to it. So this is one way to take a look. And if you want, you can type in the chat or give a thumbs up to the site if you are quantum secure, or a thumbs down if it says you are not quantum secure. It's a fun way to engage. Now, another thing that you can do is you can actually type in other websites. So I'll just type in google.com. And this will go check to see if they are offering to negotiate quantum safe security on them already. And so google.com, you can see here, is offering post-quantum security algorithms. And you may be surprised as you type other things in here to understand whether or not they have the algorithms in place. Because what's happened is one of the CDNs, Cloudflare, has added this technology by default to many of their customers. And so if you go to the site, you may be pleasantly surprised to see that it is post-quantum enabled. However, even that company may not have taken any action. Cloudflare, we scanned the top 1 million websites. We found about, I think it was 27% or so of them had already post-quantum protections enabled on their .com sites. And that's because people have taken the initiative to start upgrading the internet to be using these algorithms. Google is another one that has famously added this to many of their properties as well. And then the last thing that this site has is the ability to search for different products that have taken the initiative to add some type of post-quantum security capabilities to them. So you can see here Cisco has added capabilities to some of their router technology, and you can go through and read more about it. There's tons of Cisco products, so obviously they haven't gotten to all of them, but many of the, but it's important to start knowing and being aware of what you're buying, what you're using, and where it's being advanced. So yeah, Nginx, another web server, has the technology available. Okay. So this is one demo I wanted to share. All right, question.
Yep. Question came through. Do you know if IIS crypto is updated for this?
Ooh, I do not know that off the top of my head. So this would be the Microsoft web server IIS. I don't know if they have a library out. That's a good question. It definitely, we can type in Microsoft here and see.
Just for
No,
giggles, I decided to
Chrome.
check to see if the government was using post quantum. Sadly, no.
Yeah, um, that's unfortunate. But they will, I believe, start to progress to adding them. I think the mandate right now is you have to do discovery and you have to have action plans, but I don't know if they actually are required to have it deployed. Okay, so that's one demo. Another one I'll share is
Carl,
this
just a
one.
reminder, we are about 5 minutes out. So after this, you might want to have any closing comments you've got.
Sure. So I'll go through this one pretty quickly too. This is about liboqs, or lib open quantum safe. This is now a Linux Foundation project. And you can just type in liboqs if you want to find it. But this is a tool set that's open source and publicly available that implements all of these algorithms and makes them available for you to use. And so just showing this capability, because I can say, ISACA Tulsa, and show that I can generate a new certificate for, whatever I want using this library, and it's using MLDSA 44, which is the new cryptographic method, as well as P520, P256, which is a current cryptographic primitive elliptic curve. And I've just created a key that uses both of these. And this was the commands that I used to create this key, and then also sign a subsequent key, so creating a chain of trust. And you can sign subsequent keys or have the subsequent keys be different types of signatures as well, to depending on if you want your CA to be using one type or your central certificate signing authority to be using one type, and a server or an endpoint to be using a different type because of the key lengths and different sizes and complexities of the keys. But this is how you can create chains of trust. And here you see, with just to push a couple buttons and 6 commands, I was able to run this and build this today. So this isn't impossible for developers to adopt and start doing and start making available. In addition, I'm just going to make a new one with just a regular RSA key and start a local host server, and then connect to that server using one of the algorithms. And you'll see that I was able to successfully generate the digital certificate and then use a key encapsulation mechanism, this Kyber 768, and connect to this web server. And you see the certificate show up that I was able to connect, and validation that, I just stood up the server and there were 2 hits. This left window and this right window were able to connect to it. And so this technology is available now for use, for testing, for prototyping, for even production deployment, as you're seeing in the Is It Quantum Safe website in the browser. So, don't be afraid to engage with these libraries, with this ecosystem, start understanding what it is, where people can be educated on it, and begin the transition period of adopting it into your different products and capabilities. So with that, I'll stop here and take any final questions.
That's great. Thank you, Carl. All right. With that, I don't see anything in the chat at the moment, but if anyone wants to come off mute for a moment, please feel free. We have another couple of minutes.
I guess the one other thing that I can talk about is the quantum economic advantage calculator that we built with MIT. So this is, if you're interested in modeling these future, the future power of quantum computers, this is a tool that you can use to do it. So if you come to this tool, you can look at integer factorization and say the Google superconducting quantum computer hardware, and when will that hardware provide economic advantage, speed advantage, economic advantage. And then if you come up here to the 10 to the 3.2, when it will actually be able to break our current cryptography. So for this device, the timeline estimates that it could be in 2031 or 2032. Within this tool, you can change all of your considerations. If you don't believe that their roadmap will scale how it will, if you believe that they've come out with a better ratio or algorithm in order to enable quantum computation, then you can adjust that and make the modifications in here and build your own predictions as well. So this is one way that we're trying to make it easier to understand when when some of these events will happen.
Yeah, that's a great tool. Again, I could see some leadership looking at that, and it helps tell the story. So that's nice to know. All right, Carl, I haven't seen anything else in the chat. I do want to say thank you so much for coming and chatting with us about this. It's been great. I've learned a ton. I hope everyone else has. If there's anything else that comes up, do we have any way of reaching out to you if we have questions?
Yeah, absolutely. I'll put my email in the chat, and I love this topic. I'm happy to talk about it and share our experiences doing strategy, doing discovery, or building applications and getting them started.
That's great. Thank you, Carl. I appreciate your time. Everyone, we thank you so much for joining us. The ISACA chapter will have a meeting on December 6th, I believe, or 12th, actually, I'm sorry, the 12th, where we'll be chatting with one of our penetration testers. So I appreciate it so much. Thank you so much for your time, everybody. Carl, again, thanks so much for joining us. We really do appreciate it.
Thank you very much.
Thanks, guys. All right, bye.